Okay, let's unpack this. We are diving into a mystery that is, well, over a century old now. An event so powerful it literally shifted how scientists thought about cosmic threats. Yet it happened in one of the most remote, almost forgotten places on Earth. We are talking, of course, about the Tunguska Event, June 30th, 1908. For you listening, just try to imagine this. A colossal cosmic explosion that, just like that, in a flash, flattened something like 80 million trees.
80 million? That's just staggering.
It is, across maybe 2,150 square kilometers, a pretty untouched Siberian forest. I mean, that's an area easily larger than many major world cities like metropolitan New York or London.
And the central paradox, right? The thing that makes this the ultimate scientific cold case is the fact that despite being the largest known impact event in recorded history, it left no crater. None.
Exactly. It's like the ghost of a natural disaster.
That absence of an impact crater combined with just the sheer undeniable force of the blast, we're talking something that rivaled a thermonuclear weapon. Right. That's precisely what kept this a global enigma for, almost 20 years. And, it still fuels some truly wild, persistent hypotheses even today. Our mission here really is to move beyond the science fiction, though we'll definitely get into those exotic theories and give you the complete, scientifically grounded story. We want to tell the whole story, everything that's in it.
Yeah, we've pulled together everything needed for a really thorough understanding. We've got historical accounts from the few people who were there, modern computer model into the blast physics, deep ecological studies looking at how the forest recovered.
And, of course, contemporary planetary defense research. It's all here. We're going to cover everything. I mean, everything. From that moment the sky seemed to split open over Siberia to those bizarre glowing skies people saw way over in Europe.
And how this single incident fundamentally changed how we look at the potential threats looming just over our heads. Okay, let's start right at the beginning. Let's set the scene for this incredibly dramatic event. We're in the remote Kodkamanaya Tunguska River area. It's eastern Siberia.
Deep in the taiga, yeah.
Right, the taiga, which is, the definition of sparsely populated. Swamps, dense large forests.
Wild.
It's wild.
Very.
And it's the morning of June 30th, 1908. Around 7:15 a.m. local time. So what was the very first sign that something truly extraordinary was happening?
It began apparently with this incredible light show. Eyewitnesses, and they were scattered over hundreds of kilometers, they reported seeing this brilliant blue-white fireball streaking across the northern sky.
Moving fast.
Oh, yeah, reportedly moving very fast, leaving this trail of smoke and, glowing particles behind it. And this was followed almost immediately by an intense flash of light. Some people described it as being brighter than the sun.
Brighter than the sun. Wow. And then the sound. The atmospheric entry wasn't quiet, I imagine.
Not at all. It was followed by this cataclysmic, deafening boom. The sonic phenomena were just staggering. The noise was heard by thousands of people, reaching incredible distances.
How far are we talking?
Well, for instance, the explosion was registered acoustically up to 800 kilometers away in a city called Kansk. And actually, the speed of that sound wave helped modern scientists later reconstruct the probable height and location of the detonation. It was a key piece of data.
And we have these incredible eyewitness accounts that survived, right?
Yeah.
Almost mythological sounding, mostly from the few Russian settlers scattered around and the local indigenous Evenenki people.
Yes, those accounts are invaluable. One of the most important testimonies we have comes from a witness named S.B. Semenov. He was situated about 65 kilometers away, that's roughly 40 miles, near the Vanavara trading post, which, mind you, was barely touched by the main devastation.
And what did he see? Or hear?
He described the sky literally splitting in two, and fire appeared high and wide over the forest. But he also reported something else crucial, an immediate and powerful thermal pulse, heat.
He felt scorching heat from 40 miles away. That detail, that always gets me. It's just incredible.
Yeah.
Absolutely. He specifically noted his shirt felt as if it were on fire. And then the massive blast wave arrived, throwing him clean off his porch and shaking the ground violently.
So that confirms it wasn't just a pressure wave. There was this huge release of thermal radiation first.
Precisely. It preceded the physical pressure wave. That thermal flash was, standing way too close to a colossal fire, only it happened instantly, miles away.
Okay, so what about the people who were closer? Closer to ground zero?
Those who were closer, say within the 30 to 40 kilometer range of the epicenter, they suffered much more direct consequences. Reports say they were tossed into the air, thrown against things, or knocked unconscious by this sudden, just overwhelming pressure wave.
Buildings, too.
Oh, yes. We know several log cabins and other structures were immediately blown apart. But although the destruction was vast, the region was just so incredibly sparsely populated that large settlements were spared. That's why the human toll was, statistically speaking, minimal.
Minimal meaning.
Maybe 2 or 3 speculative deaths, but none were ever officially confirmed, mostly because there just wasn't the infrastructure out there for that kind of record keeping back then.
But even if the loss of human life was statistically small, the tragedy for the local inhabitants, the Yuvingki people, was immediate and devastating in a cultural and economic sense.
That's such a vital point. The local Eventi population, they lived this pastoral life, herding reindeer. They were deeply reliant on the taiga ecosystem and their animals.
So the blast would have hit their livelihood directly.
It destroyed their entire economic foundation. Massive herds of reindeer grazing near the blast zone were, well, instantly incinerated by the thermal wave or killed by the shock wave. Gone. The survivors later talked about the event as Ogdi's fire.
Ogdi.
Yeah, linking it to their powerful god of thunder. It shows how quickly this cosmic event was sort of absorbed into their folklore as this act of powerful, destructive, maybe divine agency.
But the truly staggering element, maybe, is that this wasn't just a local Siberian tragedy. The blast registered its presence.
Wow.
Well, across the entire planet within hours, didn't it?
That's absolutely right. That's where the scientific record really picks up the story. Within the hour, the seismic signature of the explosion was registered on seismographs all across Eurasia.
Like an earthquake.
Exactly like one, indicating tremors equivalent to about a magnitude 5.0 earthquake. These instruments, they're designed to detect movements in the Earth's crust, but they were picking up the massive ground vibration caused by the atmospheric shock wave hitting the Earth.
And this leads us to the effects on the atmosphere itself. We know the barometers, the instruments measuring air pressure, showed disturbances globally.
Yes, that's key. We actually had quite advanced microbarographs operating back in 1908 in places like St. Petersburg in Russia and even London, England.
Really, in London?
Oh, yes. These sensitive instruments recorded these abrupt, massive spikes in air pressure. It confirmed that the physical shock wave generated by the Tunguska explosion traveled outwards and literally circled the globe, registering its presence thousands of miles away. It genuinely shook the atmosphere of the entire planet.
Okay, here's where it gets really interesting, almost weird. The visible effects on the sky afterwards. For days following the blast, the skies over Europe and Asia looked, well, completely alien.
This is the famous anomalous twilight or bright nights phenomenon, an absolutely bizarre effect that captivated millions of people across the northern hemisphere.
How bright are we talking?
In places as far west as London, Scotland, even Western Russia, the sky glowed so intensely, even at like 1:00 a.m., that people could easily read newspapers outside without any artificial light.
Read a newspaper at 1 a.m. by the glow. That sounds like science fiction.
Doesn't it? People describe the clouds as silvery, shimmering, sometimes strangely colorful, just eerie.
So what's the scientific mechanism behind this?
Yeah.
An explosion in Siberia making the skies glow over England. How does that work?
The best explanation relies on particulate scattering way up high in the stratosphere. The high-altitude airburst basically dispersed massive quantities of fine dust, aerosols, and ice crystals.
Remnants of the object itself.
Exactly. The vaporized remnants of the impactor plus atmospheric water vapor caught up in the explosion, all thrown high into the upper atmosphere. This material then traveled rapidly westward with the atmospheric currents.
And once it's up there?
Once injected at those altitudes, this veil of microscopic particles becomes incredibly efficient at scattering sunlight. So long after the sun had set on the ground, these high-altitude particles were still catching the sunlight and reflecting it back down to Earth.
Creating that bizarre prolonged twilight effect.
Exactly. Across vast areas of the northern hemisphere. It was visible for several days until the particles eventually dispersed.
And do we have actual scientific measurements from the time that back this up, this idea of widespread atmospheric dust?
We do, actually. Astronomical observatories that were operating back then, like the Mount Wilson Observatory in California, they were monitoring solar radiation as part of their regular work. And their records show a measurable decrease in atmospheric transparency for several months following the event.
Consistent with a dust veil.
Perfectly consistent with the theory that millions of tons of dust aerosol were injected high up into the atmosphere, reducing the amount of direct sunlight reaching the surface. So this atmospheric disturbance wasn't just anecdotal, it was a physical, measurable consequence of that massive cosmic body detonating miles above the taiga.
So in those first few days of July 1908, The world was quietly given this irrefutable proof of a monumental cosmic event, even if nobody really understood the cause for decades.
Precisely. The evidence was there, written in the sky and on scientific instruments, just waiting to be interpreted. So the primary evidence for the Tunguska event, maybe paradoxically, doesn't come from human records or, artifacts. It comes from the signature left indelibly on the Siberian landscape itself. And this physical signature is what allowed scientists decades later to basically reverse engineer the explosion.
And that signature is one of just catastrophic radial devastation. Let's quantify the scale again, because it's hard to grasp.
It really is overwhelming. The blast wave leveled an estimated 2,000 to 2,150 square kilometers of forest. That's roughly 830 square miles. About 80 million trees knocked down flat.
It's like completely leveling a circle of forest about 50 kilometers across, right?
Roughly, yes, a huge area.
Yeah.
But the pattern of the fallen trees is truly the single most important clue. It's not just that they fell, but how they fell.
Right, the radial pattern.
Exactly. The trees lay with their tops pointing radially outward from a very precisely defined central blast area. It looks exactly as if, a giant wind flattened the forest in an instant, just sweeping outward from a single point above the ground.
That outward direction is key.
Crucial. And furthermore, the signature was complex. It wasn't just a pressure wave. There was intense thermal radiation, too. Investigators found widespread charring and evidence of fire starting near the epicenter. That confirms that a really potent pulse of heat swept across the area alongside, or maybe just before, the air pressure wave.
Okay, this brings us back to the defining feature of the event, and maybe the most confusing element for those early investigators like Kulik. The complete absence of an impact crater.
Yeah, the lack of a conventional crater is the absolute master key to the whole mystery. It confirmed definitively that the object never reached the ground intact. It didn't hit the ground as one piece.
So it must have broken up.
Oh, more than broken up. It experienced a catastrophic, incredibly rapid deceleration and explosive fragmentation in midair. The scientific consensus now places the burst altitude somewhere between 5 and 10 kilometers above the surface, about 3 to 6 miles up.
And exploding that high up meant...
It meant the object was effectively pulverized into superheated dust and gas, which ensures that only tiny fragments, if any, ever actually reached the taiga floor. No big pieces left.
And the blast pattern itself, you mentioned, is unique to this kind of aerial detonation. It's different from a surface explosion. We need to dig into the famous telegraph poles phenomenon.
Yes. This is the definitive hallmark of the airburst theory. Right near the epicenter, in an inner zone maybe spanning about 8 kilometers wide, the trees were not knocked down sideways.
They were still standing.
They remained standing upright, yes. But, this is the bizarre part, they were completely stripped of all their branches and bark, and they were scorched black where they stood. Kulik's teams, when they first saw them, nicknamed these bare trunks the telegraph poles.
Okay, that seems deeply paradoxical. How can the center of the blast be less flattened than the area further out? If the blast was so massive, why weren't those central trees also blown flat?
It's a spectacular illustration of airburst physics and geometry, really. When a really powerful object detonates high in the atmosphere, the shockwave propagates outward spherically, like an expanding bubble.
Okay.
Right underneath the detonation point at the core area, the blast pressure hits the ground almost entirely vertically, straight down. Now, this downward force is strong enough to crush, snap, and scorch the trees from above, stripping them clean, but it doesn't necessarily push them sideways.
I see. So the force is mainly downwards there.
Exactly. But as the shockwave expands farther out, its angle changes. It begins to travel more horizontally across the ground, and that's where it hits the trees laterally, applying the maximum horizontal force, which causes them to blow over flat to the ground in that huge radial pattern we talked about.
So the standing, scorched poles right at the center, and the horizontally felled trees further out. They're essentially a perfect physical diagram of a massive overhead explosion, like a footprint of the blast shape.
Absolutely. That precise geometric pattern, the vertical blowdown at the center surrounded by the radial felling, was actually later successfully replicated in scale model forest tests. Soviet scientists did this in the 1960s.
They blew up model forests.
Essentially, yes, using conventional explosives to simulate the airburst. And those tests provided the ultimate verification of the airburst theory over, say, a ground explosion or other potential sources. It matched perfectly.
Okay, and we need to make sure everyone listening really grasps the sheer power involved here. What are the modern energy estimates for the Tunguska blast? How big was it?
The estimates, which are derived from analyzing the scale of the tree-felling zone and also those seismic and barometric readings we mentioned, they place the energy release somewhere between 10 and 30 megatons of TNT equivalent.
10 to 30 megatons? It's worth just pausing on that number for a second. That energy estimate means the Tunguska Event was hundreds of times more powerful than the atomic bomb detonated over Hiroshima.
It's a sobering comparison, isn't it? This was kinetic energy released on the scale of a mid-sized thermonuclear weapon, just detonating miles above the Siberian taiga.
And even if we take the lower end of that estimate, say 10 megatons,
That's still an absolutely astounding natural force, and because the energy was released relatively low in the atmosphere, 5 to 10 kilometers up, it maximized the damage at ground level across that huge area. The Tunguska event still remains the largest documented example of a hypervelocity atmospheric explosion in history.
it also gives us some pretty chilling context for the near-miss aspect, doesn't it? I mean, that impactor had arrived just a few hours later.
Yeah, the rotation of the Earth would have placed the epicenter directly over, say, St. Petersburg in Russia, or potentially even further west, into densely populated parts of Europe. The consequences, well, they would have been truly apocalyptic. Unthinkable, really. So, despite this clear evidence of a catastrophic, potentially civilization-altering blast, the actual scientific investigation into Tunguska didn't really get going until nearly 2 decades later. This long delay is a fundamental part of the whole Tunguska mystery narrative.
Right. Why did the world let such a colossal event just sit there, uninvestigated, for so long? I mean, 20 years is practically an eternity in scientific terms.
Well, there were several overlapping historical factors that created that vacuum. Firstly, you just can't overstate the geographic remoteness of the Podkamennaya-Tunguska region. Travel and logistics were an almost insurmountable task, even in the best of times back then.
Yeah, remoteness. What else?
Yeah. But maybe more significantly, the world was very quickly engulfed by World War I. And that was followed almost immediately by the Russian Revolution and the devastating Russian Civil War. So scientific focus, funding, manpower, it was all simply redirected towards survival and military concerns. Science took a backseat.
So the mystery literally just sat there undisturbed, waiting in the vast Siberian wilderness, while the world basically tore itself apart.
Precisely. It wasn't until 1921 that the Soviet Academy of Sciences finally began to act. They were spurred on by those tantalizing early reports from locals and a few scattered newspaper accounts mentioning a possible giant meteorite fall.
And that's when they dispatched the man who really becomes central to this story.
Yes, the man who would essentially dedicate his life to the case, the Soviet mineralogist Leonid A. Kulik.
Kulik, he's the key historical figure here. What was his motivation, and what happened during his first attempts to actually reach the area?
Well, Kulik was, you could say, a traditionalist in his thinking. He was absolutely convinced that this was a conventional, large nickel-iron meteorite that had physically struck the Earth. His main motivation was finding that, priceless metallic remnant for the Soviet state, a big chunk of space rock.
But his first expedition failed.
His 1921 expedition, yeah, it was a failure. Despite getting local accounts of the blast, the combination of terrible weather, disease among his team, and just the vast, impenetrable, swampy taiga forest, it proved too challenging. He had to turn back before even reaching ground zero.
But he didn't give up. It wasn't until his second expedition in 1927 that he finally managed to penetrate the wilderness and make the real scientific breakthrough.
Yes, and the experience sounds physically harrowing. Kulik and his team travel hundreds and hundreds of miles, often by riverboat and then just on foot, battling swarms of mosquitoes, logistical nightmares. It was incredibly tough.
And when he finally got there,
Yeah.
even after 19 years,
The scene was still astonishing. He described mile upon mile of felled trees, confirming that radial pattern of destruction everyone had talked about. He wrote about encountering this vast flat circle where the trees lay with their tops pointed away from the center. And his team immediately confirmed that bizarre telegraph poles effect right at the very heart of it.
but his initial hypothesis, the idea of a big iron meteorite, it colored his entire search afterwards, didn't it? It led him down a logical path, maybe, but ultimately the wrong one.
That's exactly right. It's the tragic irony of Kulik's incredible work. He saw the devastation, but because he was expecting this huge metallic body, he focused all his meticulous searches entirely on finding a large impact crater and the fragments that should be in it.
He spent incredible amounts of time and effort trying to locate and excavate what he thought were potential impact pits, didn't he?
He did. I remember the source detailing his discovery of those small circular bogs in the central zone. He must have been absolutely convinced he'd finally found the crater, or at least secondary craters.
You can imagine the excitement.
Oh, absolutely. He found several of these small, circular, water-filled bogs. He thought they were small craters formed by fragments that broke off. His team devoted considerable resources to trying to drain and excavate one particular pit, which they nicknamed Suslov's Crater. But as we now know, the persistent digging only yielded disappointment. They eventually found an old tree stump and thick layers of peat at the bottom, confirming it was just a natural sinkhole, probably a thermokarst feature common in permafrost regions, not an impact site at all.
And he led more expeditions after that, still searching.
3 more, yeah. All the way up to 1938, still convinced he'd find that physical impactor. It must have been incredibly frustrating for him to keep confirming the massive blast evidence, but finding absolutely nothing solid to explain it.
It was a monumental effort, though, spanning over a decade. And it culminated in the first aerial survey of the central blowdown zone in 1938. Right.
Yes, that aerial survey was revolutionary for its time. It provided the first large-scale photographic confirmation of the radial pattern from above. But tragically, those irreplaceable aerial photos were later lost in a fire at an archive in 1975, which remains a huge blow to the historical scientific documentation of the event.
But here's the critical pivot, isn't it? Kulik's failure to find a crater or large metallic debris ultimately forced a major paradigm shift in science. His negative result was actually incredibly important.
Absolutely. His meticulous, decades-long, but ultimately fruitless search laid the crucial intellectual groundwork. Scientists, looking at his data, had to gradually conclude that the Tunguska event was not a conventional impact. It had to be something else. A catastrophic atmospheric explosion, a massive airburst.
The object disintegrated violently before it even hit the ground.
Exactly. So Kulik, despite tragically dying in a German prison camp during World War II, without ever solving the mystery he chased for so long, he is the foundation upon which all the later airburst modeling was built. He effectively proved what it wasn't, which allowed future generations to finally prove what it was.
Okay, so the early 20th century expeditions, mainly Kulik's work, confirmed the vast devastation and, crucially, the lack of a large impactor or crater. But to move beyond just the airburst theory and actually identify what the object was made of, scientists had to wait decades, really, for analytical technology to catch up.
Yeah, what's fascinating here is the sheer shift in scale that was required. When the macroscopic evidence, the big crater, the large fragments was missing, scientists had to pivot entirely to the microscopic level. They needed to find the cosmic DNA, essentially hidden in the dust and soil.
So if the original object, maybe 50 meters across, was completely vaporized in the airburst, what tiny traces could it possibly have left behind for later investigators to find?
Well, the real breakthrough came primarily from Soviet expeditions conducted between the 1950s and the 1960s. They started doing really meticulous work, taking coarse samples from the peat bogs in the area and carefully sifting through tree resin collected from near the epicenter. They were looking for microscopic smoking guns. And they found them. Tiny, metallic and silicate spherules. Little balls generally measuring less than 0.5 millimeter across, so really small, 0.1 to 0.5 millimeter, embedded within the layers of peat that corresponded precisely to the year 1908.
Like tiny ball bearings from space.
Sort of, yeah. Essentially cosmic microdust particles that somehow survived the intense heat and vaporization of the main blast.
Okay, but how did they confirm these were definitely extraterrestrial? Couldn't they have been, I don't know, local volcanic ash or maybe even industrial contamination from somewhere?
That's the key question, and the answer came from chemical analysis, which provided the definitive signature. Specifically, it was about the elemental ratios. These tiny spherules contained unusually high concentrations of 2 elements, iron and nickel.
Iron and nickel. Meteorites often have that, right?
Exactly. Crucially, the ratio of nickel to iron found in these microspherules is characteristic of extraterrestrial material, particularly stony meteorites called chondrites. It's vastly different from the ratios you find in typical Earth rock. They also often contain traces of cobalt, another indicator.
And the distribution of these spherules also helped confirm the airburst theory, didn't it? Where they found them mattered.
Yes, absolutely. The geographical pattern was perfect. These nickel-rich microspherules were found to be densest right near the identified epicenter, and then their concentration tapered off rapidly as researchers sampled further and further away.
Consistent with fallout.
Entirely consistent with fallout, dusting the ground directly underneath an overhead explosion that had pulverized a meteoroid, like fine ash settling downwind from a fire.
Now, I recall the sources also mentioned the search for isotopic evidence, which sounds much more nuanced, maybe more challenging.
That's a crucial area of ongoing research, yes, particularly work done in the 1990s. Italian researchers, for example, started analyzing the actual 1908 growth wings of surviving pine trees from the area.
What were they looking for in the tree rings?
They were looking for unusual isotopic ratios of elements like carbon, hydrogen, nitrogen. The hypothesis was that the vaporized cosmic material might have been sort of absorbed or incorporated into the tree's growth patterns immediately after the blast.
Yeah, I think iridium was mentioned too, the classic asteroid marker.
Right. Trace amounts of iridium, that's a platinum group element, extremely rare in Earth's crust, but much more abundant in asteroids, were also reported in some Tunguska peat deposits from the 1908 layer.
But you said those findings have been controversial. Why is it so hard to definitively prove the presence of, say, iridium specifically from 1908?
Well, it's incredibly difficult, mainly due to the high purity required in remote sampling and the potential for contamination. Iridium is the classic marker for asteroid impacts. It was the smoking gun that helped prove the KT extinction event was caused by an impact. But the Tunguska site is really complex environmentally.
How so?
Contamination from modern industrial sources carried by wind or water, or even as natural variations in sedimentation rates within the bogs over the last century, these can lead to inconsistent results when different labs try to replicate the findings. So while the isotopic studies are suggestive, the key takeaway, the most robust evidence, remains those nickel-rich spherules. They're less prone to surface contamination than trying to measure incredibly tiny trace amounts of iridium.
Okay, so we had the macroscopic damage pattern figured out by the 1920s, 30s, the chemical microevidence nailed down by the 1950s, 60s, and then modern science had to put it all together using, what, computational power.
Exactly. We transitioned from just observation to simulation. Scientists needed to really calibrate the forces involved. Unfortunately, or perhaps unfortunately, depending on how you look at it, Mother Nature gave us a modern calibration data set.
You mean Chelyabinsk?
The 2013 Chelyabinsk meteor event over Russia, it was a much smaller event, maybe a 500 kiloton airburst compared to Tunguska's 1030 megatons. But crucially, it was extensively documented by modern instruments, dash cams, seismometers, satellites, everything.
Right. Everyone saw those videos. So how exactly did Chelyabinsk help researchers fine-tune the models for Tunguska, which happened over a century earlier?
Chelyabinsk provided crucial, real-world data on burst kinematics. It showed us how a rocky object of a known size breaks apart in the atmosphere, how its energy gets dissipated across different atmospheric layers, and how much pressure wave is generated depending on the altitude of the burst.
So you could take the physics learned from Chelyabinsk?
Exactly. By taking the Chelyabinsk model and essentially scaling it up to match the energy levels estimated for Tunguska, 10 to 30 megatons, researchers could then run millions of computer simulations. They varied all the parameters. The object's composition, rocky versus icy, its entry angle, its speed, its initial size.
That must have been the definitive test. What did all those simulations overwhelmingly point towards as the best fit scenario for Tunguska?
The modeling converged very strongly on a specific high-probability culprit. The Tunguska object was almost certainly a stony asteroid, probably belonging to the class of meteorites known as chondrites.
How big?
Relatively small on a cosmic scale, but large enough to pack a huge bunch. Estimated diameter between 50 and 80 meters. So think roughly the size of an office building or a large passenger jet.
And its entry?
It came in steep and fast, entering the atmosphere at a breakneck speed of approximately 15 kilometers per second. That's about 55,000 kilometers per hour or over 34,000 miles per hour.
Wow. And that combination, stony composition, the speed, the mass, that explains the final explosive moment.
It does. The models show that a stony body of that size hitting the atmosphere at that speed would experience absolutely massive dynamic pressure during entry. This leads to violent, catastrophic fragmentation at a key altitude somewhere between 8 and 14 kilometers up.
And that fragmentation's the explosion.
Essentially, yes. The rapid deceleration and disintegration releases that enormous kinetic energy as heat and a shock wave, the estimated 10 to 30 megatons. And it completely pulverizes the object into dust and gas, which is precisely why Kulik never found his crater or any large fragments.
So this scenario seems to tie everything together.
It really does. It explains every major observed piece of evidence. The immense blast energy, the unique butterfly shape of the tree fall pattern, the standing telegraph poles at the center, and the lack of large debris.
So after more than a century of mystery, the scientific conclusion is pretty firm. Tunguska was a natural cosmic phenomenon caused by a mid-sized asteroid exploding in the atmosphere.
The consensus is definitive now, yes. Statistical modeling, done by organizations like the European Space Agency and others, confirms that a stony asteroidal body is the overwhelming favorite, something like an 83% probability based on the physics. And this specific class of event, the mid-sized atmospheric detonator, is now the benchmark we use when we think about planetary defense studies.
Okay, so the asteroid airburst is clearly the dominant model, the scientific consensus. But the long and frankly confusing history of Tunguska means we still have some major scientific alternatives and enduring geographical puzzles that really warrant a deep exploration. We promised to tell the whole story, right? So let's start with a historic debate. Asteroid versus comet.
Right, the comet fragment airburst theory. This was actually one of the earliest and, for a long time, one of the most elegant proposals. It was initially advanced by some pretty prominent astronomers like Fred Lawrence Whipple back in the 1930s. And it offered what seemed like a perfect solution to that core mystery, the missing crater and the lack of debris.
Why did a comet seem like such a good fit for so many decades? What was the appeal?
Well, it mainly came down to composition. A comet is essentially a fragile, icy body, often called a dirty snowball, right? It's made mostly of frozen volatiles like water, methane, carbon dioxide, all mixed up with dust and some rock.
So much less dense than an asteroid.
Much less dense, much more fragile. So the thinking was, if a body with this composition slammed into the atmosphere at high speed, it would heat up incredibly rapidly, vaporize almost completely, and explode quite high up. And crucially, it would leave virtually no solid fragments or refractory debris behind.
Which perfectly explains why Kulik couldn't find anything substantial on the ground.
Exactly. It seemed to solve the debris problem neatly. And proponents also linked it to those bizarre bright nights phenomena we talked about earlier.
Ah, right. How did they connect the comet idea to the glowing skies?
They argued that the widespread, persistent atmospheric glow seen over Europe was caused by a massive spread of fine cometary dust and ice crystals thrown high into the stratosphere by the explosion. Some even tried to link the trajectory of the object to known meteor streams, suggesting it might have been a fragment of comet ink, perhaps hitting Earth during the peak of the Beta Taurids meteor shower, which happens around that time of year.
Okay, that makes a very compelling narrative. Comet fragment, vaporizes, leaves dust, causes sky glow. It fits together nicely. Why, then, has the scientific consensus shifted so strongly away from the comet model and towards the asteroid?
Well, the primary critique really revolves around density and penetration depth. This is something the modern computer models helped resolve quite definitively. Analysis, notably by astronomers Denek Sekanina back in the 1980s, demonstrated that a loosely bound, fragile comet would likely have ablated away, basically burned up and exploded much too high in the atmosphere.
Higher than the 5-10-kilometer range.
Probably significantly higher, yes. Maybe 30 to 50 kilometers up or even more. And to achieve the specific, relatively low-altitude, focused blast required to flatten the forest in that characteristic radial butterfly pattern we see at Tunguska, you need a denser, tougher object, something that can punch deeper into the atmosphere before exploding.
So a cometary explosion, being higher up, would have dissipated its energy too broadly across the upper atmosphere. It wouldn't have produced that intense ground-level pressure wave needed to knock down the trees like that.
Precisely. The deep penetration required for the Tunguska damage pattern points strongly towards a more robust, rock-like object. And that's also supported, remember, by the finding of those nickel-rich dust spherules, which are much more consistent with stony chondritic meteorites than with the typical composition of a comet.
So, while scientifically interesting, the comet idea is now seen as less likely.
It remains a minority view, yes. Though it's worth mentioning the concept of an extinct comet, basically. A body that was once a comet but has lost all its volatile ices over time and now just resembles a rocky asteroid. That idea does sort of blur the lines between the two theories a little bit, but the mainstream consensus is definitely stony asteroid.
Okay, let's move from the object itself to the most visible, persistent geographical puzzle that, well, keeps modern expeditions going back to Siberia. The Lake Checo hypothesis.
Ah, yes, Lake Checo. It's located roughly 8 kilometers northwest of the official epicenter, and it's been the source of some pretty intense media attention and, frankly, scientific controversy. Back in 2007, a group of Italian scientists from the University of Bologna put forward a startling proposal that this small, rather symmetrical, bowl-shaped lake might actually be a crater.
A crater? Formed by what?
formed by a significant fragment of the main Tunguska object that somehow survived the main airburst and then hit the ground, creating the lake.
Okay, that would be huge if true. What specific evidence did the Italian team present to argue for a 1908 impact origin for Lake Checo?
They presented three main lines of evidence, as I recall. First, they noted the lake's shape. It was unusually deep and conical, more like a crater lake than a typical shallow Siberian thermokarst lake formed by melting permafrost. Second, they used seismic and sonar surveys to look at the layers of sediment at the bottom of the lake. They claimed the sediment layer was much thinner than you'd expect for an ancient lake, suggesting it had formed relatively recently, possibly around 1908.
And third, there was something buried.
Yes. Third, those same sonar readings purportedly identified a dense, possibly magnetic object buried beneath the deepest point of the lake bed. They speculate because the counter-evidence is quite strong, and it actually spans multiple decades of research. Critically, earlier Soviet scientific surveys conducted way back in the 1960s had already suggested the lake was much older. They measured thick sediment layers that would likely take centuries, not just 1 century, to accumulate.
So older data contradicted it.
Yes. And the debate really intensified when a comprehensive Russian study was published more recently in 2017.
And what did that 2017 study reveal? Did they use more modern dating methods?
They did. They analyzed the lake sediments using very detailed layer counting, which functions a bit like tree ring dating for lake bottoms. And they also utilized radionuclide markers, specifically cesium-137, which is an artificial isotope left over from mid-20th century nuclear weapons testing. It acts as a time marker in sediments.
In the conclusion,
The study concluded pretty definitively that Lake Checo is at least 280 years old, which makes it impossible for it to have formed in 1908.
it's okay. That seems fairly conclusive on the age.
It does. And furthermore, there's a strong theoretical argument from impact physics. Any fragment small enough to have survived the main 10-megaton airburst would likely have lost virtually all its forward velocity and most of its mass during that explosion, meaning it would be highly unlikely to possess the kinetic energy needed to excavate a deep crater when it eventually fluttered down to the ground. It would probably just plop into the swamp.
So the scientific consensus remains firm. Lake Checo is just a natural lake, likely a thermokarst feature, and the crater hypothesis is largely dismissed.
That's the current state of play, yes. Fascinating idea, but the evidence strongly points against it. So for decades, this information vacuum surrounding Tunguska, the extreme remoteness, the delayed investigation, the just sheer unimaginable scale of the blast, it made it a perfect canvas for, non-scientific speculation. And some truly spectacular exotic theories emerged.
Yeah, this raises an important question, doesn't it? Why did this specific event generate such a persistent and widespread legacy of really wild theories? I mean, spanning everything from fringe physics to aliens. What was it about Tunguska?
Well, I think because it had all the perfect narrative ingredients for mystery. You had a massive destructive event that was definitely observed by people, combined with absolutely zero conventional physical evidence left behind, no crater, no obvious fragments. Nature basically created a perfect blank slate for speculation.
And since the established scientific answer took so long to develop.
Right. People filled that void with the fantastic, the extraordinary. So let's start with some of the scientifically refuted but undeniably interesting physics-based ideas that were proposed.
Okay, first up, the antimatter meteor. Now, this is a genuinely compelling attempt to explain the total lack of debris, isn't it?
It is, yeah. It was proposed by physicists like Clyde Cowan, one of the discoverers of the neutrino, and others back in the 1960s. The theory suggested that a very, very small piece of cosmic antimatter matter with opposite charge entered our atmosphere.
And antimatter meeting regular matter.
Boom. Upon contacting ordinary matter, nitrogen or oxygen molecules in the air, it would immediately undergo matter-antimatter annihilation, a complete conversion of mass into energy in a massive burst. The real beauty of the theory was that this process would leave literally zero conventional debris behind, just energy.
That explains the missing fragments perfectly.
Yeah.
So where does the theory fall apart when you compare it to the observed evidence from 1908?
Well, it fails on two critical fronts, both related to the energy release signature. First, Matter-antimatter annihilation produces an enormous, very distinctive burst of high-energy gamma rays. And no such substantial burst was observed or reported by any astronomical observatory or witness at the time. That's a big problem.
Okay, no gamma rays. What's the second issue?
The second is the altitude issue. Annihilation would happen almost instantaneously upon the first significant contact with the atmosphere. That means the explosion would likely occur way up high, probably in the high stratosphere, maybe 50 kilometers or more up.
And an explosion that high
Would have dissipated its energy far too widely. It wouldn't produce the relatively low-level, focused shockwave required to flatten 80 million trees in that specific pattern near the surface. So the physics just doesn't match the resulting devastation pattern on the ground. Intriguing idea, but no.
Okay, then we have maybe the ultimate sci-fi scenario. The micro-black hole hypothesis, proposed in 1973.
Ah, yes. This came from physicists Albert Jackson and Michael Ryan. They suggested that maybe a tiny black hole, perhaps the size of an atom but possessing the mass of a small asteroid, struck the Earth.
A black hole hit the Earth.
Well, they speculated the Tunguska blast wasn't an explosion of the object, but rather the entry shock wave created as this incredibly dense object punched straight through the atmosphere and then passed clean through the entire Earth, exiting on the other side.
Wow. Okay, if it passed through the Earth, what evidence should they have expected to find on the far side? Where would it have come out?
They speculated there should have been a corresponding exit event, maybe a second atmospheric shock wave or some kind of disturbance, likely focused over the North Atlantic Ocean or possibly the South Pacific, depending on the exact trajectory.
Was anything found?
Intensive analysis was conducted, looking through historical records, seismic data, but absolutely no evidence of any kind of antipodal disturbance was ever found. And beyond that, the physics is problematic too. A micro-black hole passing through Earth would interact primarily through gravity. It wouldn't really explode like a bomb upon entry. It would likely deposit far too little energy into the atmosphere to cause the kind of widespread devastation observed at Tunguska. So it remains an intellectually stimulating thought experiment, maybe, but it's physically discredited as an explanation.
Okay, before we venture fully into aliens and conspiracy theories, let's cover the most plausible terrestrial explanation that was proposed at one point. The geophysical event hypothesis. The idea it wasn't cosmic at all.
Right. This theory basically posits that the explosion wasn't from space, but rather a massive natural gas detonation originating from the Earth itself. Proponents argued that an absolutely immense volume of natural gas, maybe 10 million tons of methane, could have erupted violently from the Siberian bogs or from subsurface permafrost reservoirs, which are known to exist in the region.
And this gas cloud then ignited.
Exactly. The idea was this methane would have accumulated rapidly near the surface and then somehow ignited, maybe by lightning, maybe something else, essentially detonating like a gigantic fuel air bomb.
Okay, how does science rebut the idea of a massive swamp gas bomb causing Tunguska? It conveniently explains the lack of an impactor.
It does conveniently explain that, yes. But it fails pretty dramatically when you look at the actual physical evidence. Firstly, there's just no evidence either from historical accounts or from modern chemical analysis of the soil and peat of a massive sudden gas leak like that. Nor do we see the specific chemical signatures you'd expect from a multi-megaton methane explosion lingering in the environment.
And the blast pattern again.
And most importantly, yes, the destruction pattern is the ultimate refutation. That precise, radially symmetric pattern with the telegraph poles at the center and the butterfly-shaped blowdown. That is the unique fingerprint of an overhead, point-source atmospheric explosion. A ground-based geological eruption or spreading gas leak explosion simply cannot produce that highly specific signature. The physics doesn't work.
Okay, now for the theories that really captured the public imagination over the years, the pop culture conspiracies, started with the granddaddy of them all, the enduring UFO or alien spaceship theory.
Ah, yes. This theory gained serious traction not from any scientific finding, obviously, but primarily from fiction. It was widely popularized by a Soviet science fiction writer named Alexander Kazantsev. In 1946, he wrote a short story called Explosion.
And what was the premise?
He imagined a nuclear-powered Martian spacecraft that malfunctioned and detonated mid-flight over Siberia, maybe while trying to refuel from Lake Baikal or land. And given the political climate of the early Cold War, the secrecy, the lack of official information about Tunguska, this trope of an extraterrestrial vehicle crash landing in the remote taiga just took off. It became a modern legend.
And that basic concept was heavily embraced by popular culture afterwards, wasn't it? Showing up in films, video games like Secret Files, Tunguska, TV shows like The X-Files.
Precisely. It's a very compelling narrative, isn't it? The
Mhm.
alien crash in the wilderness. But empirically, scientifically, there's absolutely zero support for it. Extensive searches across the epicenter over many decades, involving everything from Geiger counters looking for radiation to geological surveys, soil analysis, they have found no exotic alloys, no unusual metallic materials, no debris that looks remotely like remnants of any sophisticated spacecraft. It remains a fascinating piece of 20th century folklore, but it has no basis in fact.
Okay, finally, we have to mention Nikola Tesla's death ray. This one often surfaces because the timing is roughly right, 1908, and Tesla himself was a famously eccentric genius working on some pretty wild stuff.
The suggestion that the inventor Nikola Tesla was secretly testing some kind of high-energy weapon, maybe a powerful wireless energy transmission device from his laboratory on Long Island, New York back in 1908, and that he somehow accidentally aimed it towards the Arctic Circle and inadvertently caused the Tunguska blast.
Right. Did Tesla actually have any experimental capability back then that could even remotely rival a 10-megaton airburst thousands of miles away?
Absolutely not. While Tesla was indeed exploring some truly radical ideas for wireless power transmission and high-energy radio waves, historians and physicists universally dismiss this theory as pure pseudoscience. There is simply no historical documentation, none to suggest he caused any kind of explosion, let alone possess the capability to aim or deliver such a massive, focused pulse of energy over thousands of miles with the specific devastating results seen in Tunguska, including, crucially, the seismic waves and the specific meteoritic dust fallout signature.
It's just pop culture connecting two contemporary mysterious data points, Tesla's experiments, and the Tunguska event without any real evidence.
Exactly. Fun to think about, perhaps, but entirely unfounded. So, the century-old mystery of Tunguska has essentially been solved by modern science. It's firmly established now as a cosmic airburst event caused by an asteroid. But its legacy extends far, far beyond just being a historical curiosity. It fundamentally transformed our approach to planetary safety, and it also created this unique natural laboratory for ecological study.
Let's first look at the ecological aftermath.
Yeah.
What actually happened to that huge area, that 2,000 square kilometers of leveled taiga? How did the ecosystem respond over the last century?
Well, Tunguska became this absolutely unparalleled case study in forest succession and ecological resilience. Immediately after the blast, the area was basically a colossal, scorched clear-cut, devastated. However, the taiga ecosystem, while severely damaged, showed remarkable tenacity. The process of ecological recovery, or succession as biologists call it, began almost immediately.
How quickly did things start growing back?
Within just a few years, hardy pioneer species, specifically things like fast-growing birch trees and Siberian larch saplings, began to colonize the open, nutrient-rich ground left by the fires and the blast.
So the forest essentially hit the reset button, replacing the ancient trees that were destroyed with younger ones.
That's exactly right. Over the past century, the forest has largely regenerated, reclaiming most of its pre-1908 extent. If you look at satellite imagery today, you see dense forest cover across the region. But botanists studying the site can still see subtle differences.
How so?
The forest that grew up within the main blowdown zone is significantly younger and often denser. It's what they call an even-age stand of trees, and it contrasts quite clearly with the surrounding older, more unevenly aged taiga forest that survived outside the blast zone.
And scientists can actually use the trees that did survive, just on the edges, as living timelines, can't they?
Yes, it's quite extraordinary. Dendrochronology. Scientists study the growth rings of the few remaining survivor trees that were located just outside the main blast zone but were still affected. Typically, the 1908 growth ring shows this sudden, dramatic narrowing.
Indicating stress.
Exactly. Indicating acute environmental stress, probably from the shockwave damage or maybe the sudden heat pulse. And that's often followed by a period of rapid recovery or release growth in the subsequent years, as all the competition for sunlight and resources was suddenly eliminated when their neighbors were flattened.
So the tree rings provide this precise natural chronology of the event and its aftermath.
Precisely. And to protect this vital natural laboratory and allow for long-term research, Russia officially established the Tunguska State Nature Reserve back in 1995, covering the epicenter and surrounding area.
Okay, and that research on impact effects leads directly to maybe the most critical modern legacy of Tunguska. its overwhelming influence on planetary defense strategies, how we think about protecting Earth from space.
Absolutely. The 1908 event served as this powerful, albeit delayed, and frankly chilling wake-up call for the global scientific community. It starkly highlighted the fact that mid-sized city-killer objects, asteroids in the Tunguska class, roughly 50 to 80 meters in size, pose a devastating regional threat. And crucially, they don't even need to hit the ground and form a crater to cause mass destruction. The airburst is enough.
And importantly, we now have a much better handle on the frequency of such events. They're not, once in a billion year occurrences, are they?
Far from it. Current estimates suggest that Tunguska-level blasts probably occur approximately once every few centuries. The likely range is somewhere between 500 and 1,000 years, on average.
So statistically, it's bound to happen again.
It is. And the fact that the 1908 impactor missed a major population center by only a few hours of Earth's rotation, well, that was purely a matter of cosmic luck. And that realization that we dodged a massive bullet by sheer chance really crystallized the threat in scientists' minds.
And this fear, this realization of vulnerability, is what spurred the systematic global effort to actually find and track near-Earth objects, or NEOs.
It entirely motivated it. Before Tunguska was fully understood, the main focus in planetary defense was mostly on the really big extinction-level events.
Yeah.
The kilometer-plus size asteroids that could threaten civilization globally. But since the 1990s, really, the focus has expanded significantly to include these smaller, but much more numerous Tunguska-sized objects.
And that led to specific survey programs.
Yes. Programs like Linear, Catalina Sky Survey, Pan-STARRS, and now the upcoming Vera Rubin Observatory. These are all designed to constantly scan the skies, looking for objects that cross Earth orbit. They are direct descendants of the realization that the Tunguska threat is real, potentially devastating, and relatively frequent on geological timescales.
The international community has formally recognized the importance of this event for modern risk management, too.
They have. Recognizing its foundational importance, the United Nations officially declared June 30th, the anniversary of the Tunguska event, as International Asteroid Day back in 2016. And the specific goal of that day is to raise global public awareness about asteroid impact hazards and to highlight the progress being made in detection, tracking, and mitigation strategies.
And then, of course, the Chelyabinsk meteor in 2013 served as a very sharp, very modern reminder that these airbursts are not just ancient history.
Absolutely. Chelyabinsk was, remember, just a fraction of the power of Tunguska, maybe only 3% or so of the energy release. The object was maybe only 20 meters wide. Yet its shockwave injured over 1,200 people, mostly from shattering glass when the shockwave hit the city below.
So Chelyabinsk was like a small-scale, real-time demonstration.
Exactly. It was effectively a public, modern calibration of the Tunguska physics. It dramatically reinvigorated global concerns about airbursts and confirmed, very visibly, that Tunguska wasn't some historical fluke, but a predictable type of natural hazard we need to prepare for.
And ultimately, Tunguska provides the justification for moving beyond just detection towards active defense missions.
Absolutely. It justifies the massive technological and financial investment into missions like NASA's recent DIRT mission, the Double Asteroid Redirection Test.
Where they actually hit an asteroid.
Precisely. And the upcoming European Space Agency's Hera mission, which will go back to study the results of that impact. These programs are explicitly designed to test our capability to physically deflect a potentially hazardous asteroid years or decades before it could hit Earth. It's a planetary defense roadmap built entirely on the premise of preventing the next inevitable Tunguska-sized impactor from striking a populated area. Tunguska remains the scientific and conceptual benchmark for mitigating these mid-sized impact disasters. #TechOutro.
So what does this all mean? Where does this leave us? Well, the Tunguska event remains the absolute textbook example of a cosmic airburst. It was this colossal natural phenomenon that really revealed Earth's chronic vulnerability to objects from space. And it proved that planetary-scale destruction doesn't necessarily require an impact crater. Just a dense, high-speed object detonating a few miles above our heads is enough.
Yeah, the weight of the evidence now is just overwhelming. You've got the physical destruction pattern, that unique tree fall geometry, the specific chemical signature of the nickel-rich micro-debris found in the soil, and then the modern computational modeling that's been calibrated by later events like Chelyabinsk. It all points overwhelmingly towards the conclusion that a stony asteroid fragment, maybe 50 to 80 meters across, was entirely pulverized over Siberia back in 1908.
And while that information vacuum in the early decades definitely inspired decades of fantastic theories, from antimatter annihilation all the way to Nikola Tesla's energy weapon, The real story, the whole story, is one of enduring scientific curiosity, incredible ecological resilience in the face of devastation, and maybe most importantly, a truly chilling near miss that effectively launched the modern era of planetary defense.
Indeed. And perhaps the final provocative thought to leave you with is this. Tunguska proved, unequivocally, that Earth is continuously vulnerable to impacts from space, and that sheer chance, just the timing of Earth's rotation, saved a major population center in 1908. We often think of natural disasters as originating on Earth, earthquakes, volcanoes, hurricanes. But the enduring legacy of Tunguska is the powerful reminder that some of our greatest potential natural hazards actually come from deep space.
Our long-term safety isn't really assured by luck, is it? It depends on the ongoing commitment of science and technology to constantly monitor the skies, to find these objects, knowing that the next inevitable impact, maybe not Tunguska size, maybe smaller, maybe even larger, is out there waiting. We're only truly safe if we're aware and if we're ready.